Open the debate about the Great Pyramid and you'll see bold claims and blurry visuals. Great Pyramid scans cut through that noise by measuring density with particle physics, not speculation. Muon tomography counts cosmic ray muons that pass through stone and compares measured directions to a stone-only model to reveal where mass is missing. More muons than expected along a line of sight mean a density deficit, a void, corridor, or pocket, while fewer muons mean more limestone along that path. That is what Great Pyramid scans actually show, a 3D density picture assembled from many angular measurements rather than a literal photograph. It cannot read inscriptions or identify artifacts. It detects the absence of stone with statistics and error bars. Keep that frame and the current results inside Khufu's pyramid make sense without hype. Inside the pyramid, teams built a non-invasive imaging network around 3 detector types to map the internal structure. Nuclear emulsion films inside known chambers record Muon tracks with very fine angular resolution after long exposures. Scintillator hodoscopes stack plastic panels into direction-sensitive planes, counting muons continuously and electronically. Gas-based detectors positioned outside the pyramid add long slanting sight lines through the core from fresh angles. When these independent methods converge on the same density deficit, confidence climbs, even if the precise shape stays fuzzy. That is why researchers treat 2 features as robust: a corridor behind the north face chevrons and a large elongated void above the grand gallery. Start with the corridor because it shows the full workflow from hint to confirmation. A localized Muon surplus behind the north chevrons marked a discrete, gabled cavity aligned with the original entrance zone. Follow-up non-destructive tests ground-penetrating radar, ultrasonic tomography, and electrical resistivity imaging refined the geometry from different physics. A micro-endoscope then looked inside via a tiny access route and revealed a real corridor-shaped space with a triangular roof, matching the non-invasive predictions. That chain Muon hint, multi-technique refinement, targeted visual check, is exactly how non-invasive archaeology should proceed. It demonstrates that Great Pyramid Muon scan results are a screening tool that guides minimal risk confirmation rather than an end in themselves. Now to the headline feature, the big void above or near parallel to the grand gallery. Emulsion plates in a lower chamber first recorded a consistent excess of muons from that region. Scintillator hodoscopes in the same chamber confirmed the anomaly from the same baseline. Gas detectors placed outside on a different face detected the same surplus through far longer stone paths. 3 technologies and multiple vantage lines converged on one conclusion: a sizable volume of missing stone exists above the grand gallery. What remains open is the exact internal geometry: one long cavity, a string of pockets, or layered spaces aligned on the same axis. To read the colorful plots you see online, treat them as muograms, not photos. Each pixel is a direction bin with a count of muons relative to a stone-only expectation. Warm colors typically mark surpluses, directions with fewer attenuations, while cool colors mark deficits. Spatial resolution depends on detector area, exposure time, and the angular acceptance from the detector's position. Inside thick masonry, resolution lives at tens of centimeters to meters. You can state corridor scale void here, but not there is a staircase with steps. That is why responsible papers report sizes as at least with uncertainties, and why they resist over-specific architectural claims. So what do these Great Pyramid scans change in the engineering story? First, they strengthen the case that major openings in mass masonry receive relieving spaces to redirect loads. The corridor behind the chevrons sits exactly where you would expect stress management above the original entrance. Second, they constrain how the core above the grand gallery was organized. A long void aligned near a steep internal passage forces design explanations beyond a uniform rubble fill. That might be construction staging, weight relief, or a sealed logistics space left after block handling, none exotic, but all structurally meaningful. Here's the physics in plain language. Muons rain down from the sky at predictable rates and angles. A detector logs the directions muons arrive from while the pyramid sits between sky and sensor. If stone is thick along a direction, fewer muons make it. If a cavity lies there, more get through. By comparing measured counts to a stone-only model, analysts flag directions with statistically significant surpluses. With 2 or more detector stations, those flagged directions are back-projected to intersect in 3D, mapping the candidate void volume. Because the signal is statistical, confidence grows with time and area. Large detectors collect more tracks per unit time, shrinking uncertainties on each angular bin. Longer exposures smooth the noise and harden true features. Multiple baselines reduce ambiguity from any single vantage. That is why new campaigns aim to add detector area and viewpoints to sharpen the big void's outline. It is also why nothing found at one location in the past does not rule out a feature detectable today from a better angle. A common misunderstanding is to ask muography to answer questions it cannot. Muon scans cannot label materials by type when total thickness is the same. They cannot tell whether a void contains air, sand, or collapsed debris. They cannot, by themselves, assign cultural function to a space. They can decisively answer, is a void of at least this size present in this region? They can rank targets for minimal risk follow-up and argue against drilling where data show nothing. Used that way, cosmic ray imaging protects heritage while increasing knowledge. What about earlier attempts that reported no chambers in other pyramids? An early landmark used spark chambers in a neighboring pyramid to search a defined region and saw no hidden rooms within its coverage. Methodologically, that result set expectations for limits and showed that high-energy physics could operate in monumental archaeology at all. Modern instruments have better angular precision, larger active areas, and vastly improved analysis pipelines. That is why today, as Great Pyramid scientific study resolves a corridor and a gallery-scale void that earlier rigs could not. The arc from null within limits to convergent detections with multiple methods is a normal scientific trajectory. How should viewers evaluate new claims about hidden voids or chambers? Ask where detectors were placed and how many viewing angles were used. Check whether more than one detector technology saw the same anomaly. Look for non-Muon corroboration radar, ultrasound, or endoscopy where safe and ethical. Verify that uncertainties and geometric assumptions were published for independent checking. Be wary of reconstructions that exceed stated resolution or assign functions without physical evidence. Trust convergence across methods more than dramatic single-instrument visuals. What do the present results imply for ancient Egyptian engineering? They suggest deliberate internal zoning to manage weight and protect low passages. They hint that builders left sealed volumes where temporary staging, ramps, or stress control once mattered. They show that predictable physics, not romantic mystery, is the path to new internal constraints. They remind us that masonry can be both massive and subtly hollowed where forces demand. And they reposition non-invasive archaeology as a long-term monitoring tool, not a one-off reveal. In that light, every careful scan adds structural context rather than cinematic surprise. Where do Great Pyramid scans go next? Bigger telescopes with near panoramic acceptance can collect orders of magnitude more muons and produce true tomographic reconstructions. Stage detector moves around the exterior, can fill angular gaps and collapse shape ambiguities. Co-registered radar and ultrasound can harden boundaries at the edges of a Muon-defined volume. Air sampling and dust analysis via micro-endoscopes could distinguish open air from sealed debris without destabilizing blocks. Public release of geometry, counts, and inversion assumptions will let independent teams validate results quickly. That is how high-profile heritage science stays credible and cumulative. So, what do Muon scans really show inside the Great Pyramid? They show where dense stone isn't, with enough precision to map a real corridor behind the north chevrons, and to require a large elongated cavity above the Grand Gallery. They do not reveal contents or fine details. They do deliver testable silhouettes that structural hypotheses must respect. They replace speculation with constraints and replace invasive look and see with targeted, reversible checks. If you want the cleanest takeaway for your viewers, Great Pyramid Muon scan results are density silhouettes with statistics and cross-checks, powerful for structure and cautious for interpretation. That blend physics first. Conservation always turns a world monument into a long-running scientific instrument rather than a one-time mystery. If this evidence-first tour helped you read the images without the hype, stay with us. Next, we'll build a simple viewer's guide to muograms and a side-by-side 3D map of viable internal layouts, so you can see which models fit the data and which don't.